Okay, so in this screencast, we're going to introduce hypothesis testing for population proportions. We use hypothesis testing to test a hypothesis. We use confidence intervals to estimate a population proportion, but sometimes we don't want to estimate it, we want to compare it to a known value or test a hypothesis about it. So if we're running for election, we want to know, are more than 50% of voters planning to vote for candidate X? We're not trying to estimate the proportion planning to vote for our candidate. We just want to know, is it more than 50%? Or we want to know, is it true that more than 90% of our patients are satisfied with their experience? Or will more than 5% of consumers seeing this ad try our product? So we're trying to compare an unknown proportion to some fixed number that we are interested in, 50%, 90%, 5%. So let's just look at an example. A pollster interviews 1,000 randomly chosen voters and finds that 520 of them are planning to vote for her candidate. And we're going to ignore just all the real-world difficulties in getting a true random sample of the voters. They're a real mess, and it makes political polling horrible, and we're just focusing on the theory and on the math for now. Okay, so does that 520 out of 1,000 provide evidence that her candidate is winning? In other words, is the proportion of all voters who support her candidate more than 50%? What she's found is a sample proportion of 0.52 and a sample size of n equals 1,000. Okay, so 0.52 is greater than 0.50. So that sounds like she's winning, but maybe that was just random variation. If the race is actually tied, then the sample proportions you get will vary. And so maybe it's not surprising that it'd be 0.52 in a tied race. She could be even losing by a little bit and come up with a sample proportion of 0.52. So we ask this question. If P is equal to 0.5, so if the race is actually tied, would it be surprising or not surprising? How likely is it that in a sample of 1,000 voters, we would find a sample proportion of 0.52 or more? Would that if the race is tied, would finding 52% out of 1,000 be surprising, if the race is tied? And if we do a simulation, it kind of suggests what the answer is. So this is a computer simulation in which a race for whatever governor is tied, and we send 1,000 researchers out into the field, and they're each going to poll 1,000 voters. So it's as if our polling is taking place not once, but 1,000 times in a race that's actually tied. And in that scenario, in that simulation, about 9.5% of the time, we got numbers 0.52 or higher. The simulation tells us that 91.6% of the time our sample proportions were less than 0.52, so about 9.5% of the time they were more than 0.52. Now this is just a simulation, but it suggests that getting 52% isn't all that unusual. Look how, what a fairly big section of it, well, about 9.5% of the time we got more than 0.52. Well, what's the exact answer? Well, if P is equal to 0.5, then the sample proportions vary. That's our sampling distribution theory. And they vary by, on average, square root of P, 1 minus P over N, or 0.0158. So if the race is tied, then you expect the sample proportions to vary by about 1.6% on average. 0.0158, that's 1.6%. And the z-score for 0.52 would be 1.26. Well, we put that into norm S dis and subtract from 1 because we want to know what's the probability of being 0.52 or higher, and we get about 0.10. Remember, a simulation gave us about 0.095 or 9.5%. The theory gives us about 10%. So the conclusion is that if the race is tied, there'd be a 10% chance of getting a sample proportion of 0.52 or higher. So that 0.52 that we observed when we went out and polled 1,000 people wouldn't be that unusual. It would happen 10% probability that we'd get a number that high if the race is actually tied. Okay, so is 10% surprising? Do we conclude that the 0.52 is what we call statistically significant, and therefore that we're probably winning the election, or not? Well, that's actually kind of complicated because it's a personal call, and we'll talk more about this in class, but the usual convention is that we need the probability, that 10%, it's called the p-value, we need that to be below 0.05 to be considered statistically significant. In other words, to be considered surprising, we need the results we got, the data we observed, to have a less than 5% chance of occurring. Now, in reality, different researchers will choose different cutoffs and will allow themselves to be surprised if they get 10%, or will require that it be 1%. But the convention, especially in statistics classes all over the country, is that it's 0.05, and so we'll take that unless otherwise specified. So in this case, we would say that we don't have enough evidence to be confident that we're winning, that the 0.52 we got wouldn't be that surprising in a tie race. And Excel is going to do the number crunching for us. So we open our procedure template, we put in 1,000 for the sample size, the sample proportion was 0.52, the proportion we're comparing it to, called the hypothesized proportion, is 0.50. This gives us that z of 1.26 automatically, and then depending on what the alternative is, well, we were wanting to know what's the probability of getting 0.52 or higher, so 0.10, that's our 10%. So here's where Excel is telling us that if the race is tied, if 0.5 is the actual population proportion, then there would be a 0.10 chance or a 10% chance of getting the 0.52 we observed, to getting that higher or higher. So we say that we don't really have strong evidence that we're winning, that the results we got, that 52% out of 1,000, is just not that unusual. Now, you might not be surprised to learn that if the sample size were 2,000, if we'd had a larger sample size and gotten that same 52%, okay, so still 0.52, but now on a larger sample size, that would be statistically significant. That would have a less than 5% chance of happening. So the 52% isn't statistically significant on a sample size of 1,000, but would be on a larger sample size. Okay, so in our next screencast, we'll talk about some more of the theory, but that's the idea. When we want to do a comparison, we say, okay, would the data be surprising? Would what we observe be surprising if there's nothing going on? We'll see more about that.